Okay, in this lesson what we're going to do is calculate degrees of freedom or calculate mobility from the kinematic diagrams that we've created. So we'll calculate degrees of freedom using Grubler's equation, and you see that on the first line here. Degree of freedom is 3 times n minus 1 minus 2 times the primary joints minus 1 times the higher order joints. And I'll explain this equation here. So n is the number of links, the total number of links, and this includes the ground. Okay. Primary joints, the total number of primary joints. These are joints that allow 1 degree of freedom. And we're going to subtract the number of higher order joints. So these are joints that allow 2 degrees of freedom. Okay? So let me try to back out what this expression means. We'll write the expression here. F is equal 3 times n minus 1 minus 2 times j p minus 1 times j h. Okay? So if I've got a plane here, I've got a plane. Okay. This plane, we'll call it an XY plane. This is for a planar mechanism. This has 3 degrees of freedom. Right? We can translate X, translate Y, and forget about this one, we can rotate Z. So we've got 3 degrees of freedom. So if we put in this plane a body, a rigid body, okay, this rigid body can move, translate in X, translate in Y, and rotate in Z. Okay? So for every body that we have, there's 3 degrees of freedom, right? So if we've got 2 bodies here, okay, 2 bodies, let's just look at this first part of the expression. It's 3 degrees of freedom for each body times n minus n times the number of bodies. Now the minus 1 is in here because we'll have to take 1 as ground. Okay, so we've got 2 bodies in this case. Okay, if we make this one the ground body, okay, we've got 2 bodies. We've got 1, 2. Okay, so the number of degrees of freedom within this system is 3 times 2 minus 1. Okay, 3 times 2 minus 1. So that's 3 degrees of freedom, which is spot on, right? This body can rotate and translate in X and Y. Okay. If we throw another body in here, body 3, okay, we've got 1 body that's ground, 1, 2, 3 total bodies, so it's 3 times 3 minus 1, so that's 6 degrees of freedom, right? This has got, this can move X, move Y, and rotate Z, and similarly this can move X, move Y, and rotate Z. Okay, so that's where this first part comes from. Okay, the second part comes from the number of primary joints. Now, primary joint takes away 2 degrees of freedom, or you can think about it as it allows 1 degree of freedom. Okay, so if I think about this from a primary joint, I'm going to have I've got 1 being the ground, 2 being this length, and I've got this joint here, A. Now this joint is a revolute joint. Think about this for a second. It only allows 1 degree of freedom. From an earlier lecture, it only allows 1 degree of freedom. Or what you can think about is that 2 degrees of freedom are taken away. Okay, so we subtract 2 degrees of freedom. So if we go back to this Grubler's equation, it's 3 times n minus 1 minus 2 times j primary. Okay, so guess what? We're taking away 2 degrees of freedom. Right? So we're removing 2 degrees of freedom for every primary joint that we have. So again, if we go back to this, we've got F is equal 3 times, we've got 2, one of those is grounded, minus 1, and we've got 1 primary joint, 2 times 1 primary joint. So we've got 3 minus 2. This system has 1 degree of freedom. Okay? Now we've covered primary joints as well as the number of links. So we've got this general expression. A higher order joint, okay, so a higher order joint, or often called a half joint, removes only 1 degree of freedom, okay? So go back to that example. Okay, we've got our link here. So this is our ground. This is our second link. We've got a joint here. We'll call this A. A allows link 2 relative to link 1 to translate as well as to rotate, right? So it allows 2 degrees of freedom, or it removes only 1 degree of freedom. So when we look at this expression here, okay, we'll come down to this system. We have F equals 3 times, we've got 2 links here, 2 minus 1, minus, we've got no primary joints, and we've got 1 half joint, okay, because it allows that. So we end up with 3 minus 0 minus 1, or a degree of freedom of 2. And this makes sense, right? This link can slide back and forth, and this link can rotate. Okay? Think about that. Now this, again, I want to say is for planar mechanisms. If we get into spatial mechanisms, okay, this is 2D, this is 3D. Okay? We're dealing over here. Second aspect of this here, if we do degree of freedom analysis, if our degree of freedom is computed to be 1, this is what is typically referred to as a constrained mechanism. Okay, here's a constrained mechanism. Okay, if our degree of freedom is 0 or negative, what we end up with is a locked mechanism. Okay, so if we compute the degree of freedom here, it's going to be 0. This is a locked mechanism. If we have greater than 1, it's what's referred to as an unconstrained or an open loop mechanism. Now, this is very common of robotics, industrial robotics. Okay, these are typically have more than 1 degree of freedom. So some examples here. If we go to this first one, let's see. Let's label this up here. We've got 1 to be the ground, 2, 3, 4, A, B, C, D. Okay, so we've got 3 times 4 minus 1. All of these are revolute joints. They all only allow 1 degree of freedom, so 2 times 4 minus 0. So this mechanism is constrained mechanism. In this case, we've got 1, 2, 3, A, B, C. So 3 times 3 minus 1, minus 2 times 3, minus 0 higher order joints. This is a truss structure. And finally what we have is 1, 2, 3, 4, 5. And then what we have is A, B, C, D, E. Okay? So 3 times 5 minus 1 minus 2 times 5 minus 0 higher order joints is equal to 2. Okay, so unconstrained or open loop mechanisms. Okay. Some additional examples here. I have computed for you the degree of freedom on this top line, and have given you the number of links as well as number of primary and half joints. I would strongly encourage you to go through these examples and see if your numbers that you work out make sense here. The other thing I would do is ask that you label these. Label and compute. And we'll go over these in class. There are some exceptions to Grubler's equation, so what you should know before, Grubler's equation only takes into account the number of links and the number of joints. it does not take into account the geometry. So mobility will not always produce correct results. Not always produce correct results. So this is a little bit of a challenge. It won't produce correct results when we've got some of these issues, and also when we take into account link geometry. So I'll give you an example here. We've got two systems that, according to Grubler's equation, and again this could be F here, in order to Grubler's equation, come up with a mobility or a degree of freedom of 0, right? So we've got 5 links, 2 primary joints, 0 higher order joints. We end up with a constrained mechanism. When in fact, based on the fact that this system links 2, 3, and 4 are all the same length, this system will actually work. Okay, and this has been shown to work. We'll talk a bit about this in class, but it won't always give you 100% correct results. With that, we'll end this lesson on computing mobility. In the next few lessons, we'll talk about common kinematic linkage types.